Hello, I am Amir Salehi. I'm at the Civil and Environmental Engineering Department here at the University of Waterloo. Today, I want to talk about a project that I working on for a couple of months now. We are trying to create a framework to estimate GHG emissions from buildings and obtain a geospatial distribution for them only using publicly available data sets to create a generalizable model. First, I'm going to quickly go through the background and highlight some points from the literature. And after that, review quickly my methodology and point out some of the future work I'm planning to do. As you know, climate change is a very big issue that we're facing. So municipalities, in order to adapt and mitigate with the climate change impacts, have also set some net zero targets for themselves to be achieved by 2050. And for achieving that, they need to conduct huge planning and actions in terms of planning their natural and built environments. And buildings, as an important part of the built environment and as a huge contributor to the global emissions, they have a 30% share in Canada, are a main sector that we have to focus on and study. There are many different actions that we can take to reduce emissions from buildings, for example, conducting retrofits, including energy efficiency measures or developing local renewable sources. But all of those actions most of them are very costly, time-consuming, and it's hard to predict their effectiveness. So we need tools to help us plan and make informed decisions. And geospatial emission distribution models can be a very useful tool for preliminary studies in the field. When I was going through the literature, I quickly noticed that there are a lot of arguments on data. So there are three main sources identified as main data sources for geospatial or large-scale building emission modeling and energy consumption modeling, which are simulated data, benchmark, and measured data. Each of them has their own problems. For example, simulating building energy consumption in a city scale, it's a very complex and data-hungry process. So in most cases, and that is impossible and doesn't lie within the scope of many projects. Measured data and benchmark data also have many issues. For example, the energy carriers are very private on their data because energy is considered to be very sensitive. And with other benchmark data or survey data that are reported, there are the question of the data quality, or because those reports are prepared by different administrative bodies, they are intended to serve different purposes, and they may be incompatible or hard to match and create a complete data set. There are also a lot of models and approaches undertaken by the scientists to create city-scale energy and emission models. But the problem is that most of them are either complex or very situation specific. For that reason, we are trying to create a framework that works at minimum level data availability to be simple and quick to be applied in any case that we want for preliminary and initial studies. Then the decision makers can decide to conduct more detailed work. And as our project is funded by Credit Valley Conservative, we are creating this framework to be applied into a more comprehensive tool named Risk and Return on Investment. And our future goal and the thing that we want to actually achieve is to apply these models into integrated climate and air models to be able to read the whole system and study the interactions of housing emission, building emission with human health and the overall system. I'm going to explain the method that I have used in three main steps. First, obviously, data gathering and pre-processing. making the estimation, and then at the end, projecting the results. So the data we need for this kind of modeling is basically two kinds of data. The climate data that here we are only using heating and cooling degree day information that is gathered from Climate Atlas of Canada, which has information about several climate models. We have used the average. And the building information, their geometry, their type, and anything that we can gather from public databases. I have mentioned the sources. As I said, the data sets are incompatible, so I had to go through different sources with different published years and try to match them all together and generate a workable data set. After that, I undergo the data pre-processing, including data cleaning, outlier detection, and data set matching. This was the most challenging part. So here's the diagram again. After that, after obtaining, I guess I went back.
Research is like that. Sometimes you feel like you're going back.
Okay.
Go ahead.
After preparing the data, I was ready to make some initial estimations. I have to say that building energy consumption is a function of hundreds and sometimes thousands of variables, and it's very hard to model. But studies show, and also the analysis that I have conducted, show that some of those features can capture most of the complexities and variabilities that exist. Here, based on the data I had, the literature and the analysis I ran, I decided that building size and the building operation type can capture most of those variability. For example, building operation type within it has hidden information about building operation hours, the equipment within the building, and things like that. Based on that, I categorized all of the buildings I had into large, medium, small, and by their operation types, office, health, education, and other commercials. I have not yet worked on residential buildings. It's just for commercial and public buildings. And now that I have all the clusters, my goal is to create a simple, generalizable model. I will estimate an energy consumption for each of those clusters, then to assign that to each individual building. So building energy sources are usually electricity or natural gas in Ontario, Canada. So we estimate the energy use intensity for both of those sources. Then, because our data sets are obtained from different years, we have to move all of them to a baseline year. I use a simple normalization process using heating degree days and cooling degree days, bringing everything to a baseline. And after that, by using governmental reported emission factors, we can estimate the emissions and continue with our modeling process. Here is a bar chart of some of the initial results that I have. It shows the mean electricity use intensity for each of my categories. This one shows the emission intensities for each of those categories, both natural gas and electricity combined. And this chart shows that if we don't make any changes to our system, what should we expect in terms of electricity use and natural gas use to happen from now to 2015 under climate change. As we expect, natural gas use will decline because this increasing temperature of the Earth's surface, there will be lower heating demand, and the electricity use will increase because there eventually will be more demand for cooling. I have to state that I have made a simplification assumption, assigning all the cooling loads to electricity and assigning all the heating load to natural gas. That should be if we have more information, we have to make that assumption more realistic. And step 3 is creating the distribution. We assign the clusters to each of the buildings we have. We estimate the emission using the floor space, and we visualize. In this one, I should have chosen a better color, But on the left-hand side, you can see the real reported emissions for public building in the city of Waterloo, and on the right, excuse me, on the right and I don't know. It's my left and my, okay, it doesn't matter. And here you can see the estimations that was made by model. Although the model is not precise, it is able to capture the patterns and the hot emission zones that can be very insightful for high-level planning. And this plot also shows that, like, although the magnitude is different and the values are different, the general trend and pattern is the same for the estimated and reductions. For the future, we want to make some improvements to our model. First of all, we have to find a way to incorporate residential buildings into the model. Modeling residential sector is harder because there are lower available data availability, and also there are more variability regarding to residential buildings. Also, like, we can increase the accuracy of the model by creating a finer lookup table, incorporating other parameters such as building height, and being more sensitive to the location of the building. And doing all of that, we plan to improve our framework and to be able to satisfy the applications that we intend to achieve. Thank you, everyone, for